Hi everyone, so if we notice in the periodic table, the atomic mass of the elements actually are in a decimal form, so it's like, 10.180 or 6.004. Well, we know that the atomic mass is supposed to consist of the number of protons and neutrons added together, and since one proton is 1 AMU and one neutron is also 1 AMU, when we add them together we should get a whole number. But we actually end up taking an average or a weighted average of all of these isotopes to figure out what the atomic mass is. So that's what we're going to be doing in this lesson. You'll need your notes as well as your calculator. So we're going to go through the definition of weighted average atomic mass, or average atomic mass. We're going to calculate them using two different methods and go through some sample questions. So here we have a neon sign. We actually saw this one in the last unit. Or last lesson, excuse me. And the circle shows a sample of the different versions of neon that we have, or the different isotopes of neon that we have. The blue dots represent neon 20 with 10 neutrons. The yellow ones represent neon 22 with 12 neutrons, and the red one represents neon 21 with 11 neutrons. They all have the same number of protons, but just a different number of neutrons. So if we know that we have, for neon 21, we have one neon 21. We have, I think, 9 neon 22, and I'm just going to estimate. I'm going to say that it's all out of a sample of 100. I didn't count, but let's just say we have 90 neon 20s. We need to figure out what the average atomic mass is, or what the average mass is of all of these. So we can't just, add up all of these and divide by 100 or divide by 3, because that doesn't give us the full mass. So, there's only one neon 21, but yet 90 neon 20s. So we can't just add them up and divide by 3. So instead, we're actually just going to add them all up and then divide by 100. So we know that if we put these into percent, for example, 1% of the sample is neon 21, 9% of the sample is neon 22, and 90% of the sample is neon 20. I put them in percents because when you add this all up, it's all out of 100. So we can show that 1% has a mass of 21. I can add that together to 9% has a mass of 22, and 90% have a mass of 20. I'm going to divide all of this by 100 because I want to get rid of that percent, right? So we don't want percent in the final answer. So if we figure all these out and solve for this, we end up getting the average atomic mass. So the atomic mass is the weighted average of all the naturally occurring isotopes of a sample. You might see this as part of a question as well. This is just rogue memorization, just a definition. Some things that they might try to kind of confuse you about, instead of just doing naturally occurring, they might say of all of the isotopes. We want just the ones that occur naturally, not the ones that are human-made. And we want to make sure that we have that weighted average in there as well. So there's two methods. We actually just saw the first method. That's the one I just showed you. And let me just show you here again in this different sample with magnesium. We have three different versions of magnesium: magnesium 24, magnesium 25, magnesium 26. And when I say version, I mean different isotopes. And if we look at the percent abundance on Earth, meaning how much is actually on Earth, we can see that 78.99% has an atomic mass, or AMU, of 23.9850. 10% has the atomic mass of 24.9858, and 11.01% has an atomic mass of 25.9826. So what we did here is we actually took the percent and multiplied it by its atomic mass and added them together. So here we have the 78.99 times the 23.9850. I just took that from this line. Then we're going to take the second line, or the second line. Let me grab a different colored pen. So 10% had a mass of 24.9858, and the third line, 11.01%, had a mass of 25.9826 AMU. The numbers, you would never have to memorize these numbers, just the method of doing it, and you'll see a graph or a table like this later on. We divided all of these by 100 because these were all in percents, and then you end up getting your final answer. So I want you to pause me right now and figure out if you can calculate what your answer is here. Alright, so hopefully you punch this into your calculator. The way I would do it is actually use those parentheses to help you. do the 78.99 times the 23.9850 in one parenthesis. Close out that parenthesis, add it up to the 10.00. By the way, if it's 0.00, don't punch that into your calculator, it's just 0. So any zeros, just zeros after the decimal point, you don't have to punch in. Then 24.9858, close out that parenthesis, do the plus sign, another parenthesis, 11.01 times the 25.9826, keep going, close out that parenthesis, then press the enter button. Alright, and then your division sign. Don't forget to divide by that 100. Now you should have gotten, well, let's see what the answer that would make the most sense would be here. So I'm going to erase some of this stuff here. If I look at the answers, I want to make sure that they all make sense. So I'm going to see that 78.99%, so almost 79%, had this atomic mass, and about 10 and 11% had this atomic mass. So if you think about the numbers, it should be closer to this first mass, which is 23.9850, because there's more of it, right? So when you make this, so when you put this into your calculator, I get 24.30501576. I'm sure it continues on. Let's figure out sig figs here. So let's take a look at our original numbers. We have 4 there, 4, 4, and then let's see, 1, 2, 3, 4, 5, 6 there, 6 and 6. So and when we're multiplying and dividing, you actually go for the least number of sig figs, multiplication, division take precedence over addition and subtraction. So we actually want to go to 4 sig figs. So we go 1, 2, 3, 4. I'm going to draw a line right there. And this 5 will actually round up that 0. So we end up having 24.31, and this is all in the units of AMU. Right? So this is one method, and I know it seems convoluted. It goes by really quickly. You guys will be experts at this soon, I'm sure. So in this method, we kept all the numbers as they were and then just divided by 100. If we notice in the second example, these are all the same numbers, but think about what we did differently here in the second method. Instead of dividing by 100, we actually took all of these percents and moved the decimal place over beforehand. So in fact, we have 0.7899 here. Instead of 10.00 over here, we actually moved the decimal place over 2 spots, so it's 0.1000, and then the same thing here. So we just moved the decimal spot over 2 places to the left. Since we've already divided by 100 for each of these before we plugged them in, don't divide by 100 again. You might see one of the two methods, use whichever one you prefer, but make sure that when you see this in multiple choice that you recognize both methods. Alright, so here are some questions. A 100-gram sample of a naturally occurring boron contains 19.78 grams of boron-10, which has an atomic mass of 10.01. I'm going to pause us here. There's a lot of reading here, so I'm just going to start writing down some stuff. So I know that we have boron-10. Boron symbol is just B, and then we use the 10 there. So 19, and so it was a 100-gram sample. So here, they didn't use percent, but we can assume it's percent because it's out of 100. So it ends up being 19, oops, let me just restart that, darling. So let's see, a 19, for boron-10, 19.78 grams has a mass of 10.01 AMU, and boron-11, which is 80.22 grams, has a mass of 11.01. So sorry that's really big, it's kind of hard to do. So I took all those numbers, put them over here. So we can assume that since it's out of a 100-gram sample that these would be our percents. If we look at the answer choices, they just want us to set it up, not solve for it. So don't worry about digging out your calculators there. But this is why I wanted you to know both methods, just in case they try to throw that in there for you. Alright, so I want you to look at each of the answers, figure out which one you think is best. Alright, so hopefully that you've seen or looked through some of these. You can see we have choice A. So they took the percent times the atomic mass and divided it by each other. That we've never done. Don't even ever choose that. For B, we have, let's see, 0.1978. So instead of dividing by 100, they put it into a decimal first, multiplied it by the 10.01, and then added that to the 0.8022 times 11.01. That looks pretty valid. Let's just double check all the rest of them just to make sure. So for C, they took, I'm going to give it a different colored pen here, 0.8022 and multiplied it by the 10.01. So they took two different samples and tried multiplying one another. That we know was wrong, and that's why I wanted you guys to kind of write out the data beforehand, because when they put it into sentences or paragraphs for you, it kind of gets convoluted or just really confusing. So make sure that you write it out like this. We can see that if they used one number from this sample and a different number from that sample, that wouldn't work. Alright, and then D, they kind of did the same thing they did with A, so we'll choose B. Alright, so here, we want the naturally occurring, the average atomic mass, and let's figure this out. Sometimes they'll give you tables like this, which is what I really appreciate, because really all you have to do is multiply that, multiply those, multiply them, and add them all together. So they want you to show the work here. So you have 27.98 times 92.22. Alright, put that in parentheses, add that to the next one, 28.98 times the 4.69, and I'm running out of space here, so I'm going to put it here. Just know that's supposed to continue off to the right. 29.97 times its natural abundance, which is 3.09. Right? I'm going to divide all this by 100 and then solve. The other option was to take the percent and then divide each one of them individually. Now, one thing that they did here, I want you to notice, is that they put the atomic mass first and then the percent. So do not, I repeat, do not put any of these numbers in decimals. Only put these numbers in decimals if you're going to, because that's the one that has the percent right there. All right? So instead, it would have been 27.98 times 0.9222 plus the 28.98 times this number in a decimal, so it's 0.0469, and add that to the next one, which was 29.97 times 0.0309. Alright, we would not divide this by 100 because we've already divided each of the percents by 100. Before you even punch this in, I want you to make sense of the data. Alright, so I'm going to erase all this. Whichever one has the greatest percent abundance, that's what your final answer should be closest to. So this one right here, this sample actually right here, has the greatest percent abundance, so your answer should be pretty close to this one. Alright? I want you to go ahead and punch this into the calculator and solve. So all my work was erased, but that gave me some space to actually write out my answer from what I saw in the calculator. So I have 28.088391, which is pretty close to this one right here. So let's think about sig figs. We have 4, 4, 4, 4, 3, 3. So go to the least number of sig figs. Go 1, 2, 3. I'm going to draw a line right there. This 8 is going to round up that 0. So I have 28.1, and the unit is AMU, or atomic mass unit. Right, and that's, again, pretty darn close to that 27.98. Alright, so to summarize, the average atomic mass is the weighted average atomic mass of all the naturally occurring isotopes of a sample. So make sure that you use either method that you prefer and punch them in correctly into your calculator. I'll talk to you guys later. Bye.